time for us to talk about problems involving vectors, which really mean we want to understand problems involving change. Now, understanding change is important, both in math, but also in life. And in both cases, the way we learn how to handle change is practice and a little bit of patience as well. And so if you're doing some practice and following along, make sure you use that pause button. See the problem and try it out. Do the best that you can. And if by chance you need my help, I'll be there to help you out. Just unpause me and I'll come join you wherever you are. So, let's begin. Our very first problem. A word problem. A 40-mile-per-hour wind is blowing due south, which means 270 degrees. You are on a plane that has bearing N 60 degrees E. Well, that should be read as north 60 degrees east. Let's draw some pictures here so we understand what's going on here. So we can set that up, and there's a wind blowing due south. Okay, so we put in our wind, and we know it's going directly south. So here's our wind coming along, blowing to the south. All right, so there's our wind blowing along, blowing south. And we're on a plane. Okay, cool, a plane. So we'll draw ourselves a little bit of a plane here. And so here's our plane. And it says the plane has a bearing of north 60 degrees east. Now the way you read this is you say, well look, start by going straight up north, then turn as though you were going 60 degrees towards the east direction. So if you think of a compass as north, east, south, west, that says you'd be heading in that way, where that's a 60-degree angle. Now you might notice it says over 30 degrees, and that would be if we went with the normal convention of using our axis here. Okay, so that's the bearing. In other words, that's the direction the plane is turned. But that doesn't mean that's the direction the plane is traveling relative to the ground. It says here that the plane is traveling due east. In other words, because of the wind, instead of moving in the direction that the plane is pointing, the movement is directly in that way. All right. So now we have sort of two things happening. The plane is moving through the air. That's that direction right there. Plane moving through the air. But the air itself is moving, and that's the wind. See, wind is all about of movement of air. So now we have two things change. How does the plane change relative to the air? How does the air change relative to the ground? And we know that that net change is going to be traveling due east. All right. Now there's some questions. What is the airspeed of the plane? In other words, how fast is the plane moving through the air? And how fast is the plane moving relative to the ground? Okay, so in other words, it's heading due east. At what speed is it moving due east? So, what is this problem involving? Well, we're talking about change. How is the plane moving as we go through the air? How is the wind moving? And you can even see that there's change showing up in the way it's phrased. Right here, do you see that? Miles per hour. That's talking about change. How many miles am I changing per each hour? Now, how do we represent everything? Well, the key here is that we can represent everything here by vectors, because this is a case where we have sort of two aspects. We have a direction where things are moving, and we have an amount by which they move. So the amount we can think of as being the relative speed. So if we update our picture here, let's clean it up. We don't have to be quite so artistic when we draw these pictures. We can think of it as there being three things. Namely, there's a vector that's going due south, and we know the magnitude of the vector, if we think of that as being the speed, would be 40. We also have that the plane, that's heading in this direction, where there's a 30-degree angle, and we don't know this magnitude yet. That would be the magnitude, that would be the airspeed. And we know that the plane is moving due east. And we don't know that magnitude yet. That would be the ground speed, how quickly it's moving relative to the ground. So, what's the key idea? Well, the key idea is to say, well, if I want to understand how I'm moving relative to the ground, I just have to add the effects of moving through the air and how the air moves. So, put another way, the vector of how the plane moves through the air plus the vector of how the plane moves through the ground gives us this vector of how the plane moves to the ground. And so in particular, our picture is not quite the right setup. What we should do is move our vectors to be in a much more convenient location. And remember, vectors can move. Vectors aren't tied to a specific space. So we can move our vector into any location which is convenient for solving a problem. So in our case, let's take this vector here and move it over to there. All right, so we're going to update our picture one more time. And let's do that. And if we do that, what we'll see is we'll see the following three vectors. How we move through the air, how the air moves, and how we move relative to the ground. You'll notice south and east mean right angles, so this is actually a right triangle. And we also know that this is a length 40 because the length corresponds to the speed, and that this angle in the corner is a 30-degree angle. And now we say, aha, what are we after? We're after the lengths of the other sides, but now perfect. Why? Because we have a right triangle. And as they say, it's the right kind of triangle, right? Where we can use our trigonometry knowledge. So, suppose we wanted to know our airspeed. Okay, so we'll use A for our airspeed. Well, what we can say is, if I know this angle, I know the opposite side, and I want to know the hypotenuse. So we could say that the sine of 30, because the sine represents the ratio between opposite and hypotenuse, is equal to 40 divided by A. But sine of 30, that's actually something that we know. Well, hopefully we know. It's certainly something we can look up. Do you know it? It rhymes with schmaff. Well, that's not a great word, right? But it's 1/2. And so now if you rearrange, what do we get? Well, move the A across, move the 2 across, we get A equals 80. And that tells us what? Well, it tells us our airspeed is 80 miles per hour. That's how fast we're flying through the air. Now, let's do our ground speed. Well, what's that? Well, we can do a couple of things. Now that we know our airspeed is 80, we can use Pythagorean theorem. So, for example, I can take the square root of 80 squared, subtract 40 squared, and that would give it. Of course, another thing we can do is say, well, let's think about triangles. I can do a cosine. I can do a tangent. Let's do a tangent just to emphasize, look, even if we didn't know what our airspeed was, we can still talk about finding this length here. The reason I say tangent, because we know the opposite side, we're after the adjacent side. Opposite and adjacent are connected by tangent. So we could say the tangent of 30 degrees is equal to our opposite, which is 40, divided by g. And g is what we're after. It's our ground speed. Do we know the tangent of 30 degrees? Yeah, that's actually something that's known. It's a nice value. Do you know it? Do you? Okay, well, that's good. So what it is that tangent of 30 degrees is 1 over root 3. Now again, cross multiply, and what do we come up with? Well, we come to the conclusion that g is equal to 40 times square root of 3. So that our ground speed, how fast we're moving relative to the ground, is equal to 40 root 3 miles per hour. And there we go. So oftentimes you'll see physics applications use vectors a lot because a lot of quantities in physics involve things that both have a direction and a magnitude. Velocity is one of them. Velocity is a little bit different than speed. Speed doesn't have a direction, but velocity does. It's not the only one. Another one which we'll see in applications is force. Force has a direction and a magnitude, which is why physics takes a lot of time. Okay, how do vectors work? What do they do? So it's an important idea to know. All right, well, one problem down. Good. Let's try another problem. So, a projectile is fired from the point 3, 7, 10 in the direction towards the point 9, 5, 1. Now, given that the projectile ends up traveling a distance of 33 units before stopping, determine at what point the projectile stopped. Now, we're not going to have anything like gravity. This is math. No gravity, everything travels in a nice straight line, and everybody's happy. All right, so how should we think of our setup? Well, let's draw a rough sketch, and I really want to emphasize the word rough. So we're in three-dimensional space. We can tell it because we have 3 coordinates. So we're in three-dimensional space, and we don't really, right now, see any reason to be very precise. So what we'll do is we'll just say, well, let's just mark 2 points. So we'll say, here's the point 3, 7, 10, and we're not going to pay, again, much attention to it being precise because we're after intuition right now. And over here we'll say is the point 9, 5, 1. So we're starting from here. See, that's where we start. A projectile is fired from. So we're coming out from here, and we're going to move in that direction. So what's happening is picture-wise, we say, look, the projectile, it's traveling somehow along this path right here. Now, that's the path on which it travels. The question is, where does it stop? Maybe it stops before we hit the point 951. Maybe it stops exactly at 951. Maybe it stops past it. Well, we don't know. That's what we have to figure out. If we knew, we'd be done already. So how do we figure it out? Well, what do we know? We know how far it travels, so we need to take that information into account. So let's think about, first off, by saying, what can we say about the direction in which it travels? So direction ties into vectors. So we know a direction because there's 2 points. So we can say, well, let's use the 2 points to give us information about the direction in which we're traveling. So we'll look at the vector here from the point 3, 7, 10 to the point 9, 5, 1. So let's look at that vector. And we look at the change from 3 to 9. That says our change is 6. From 7 to 5, that is a change of -2. 10 to 1 is a change of -9. So when we're talking about vectors, focus on change. And we say, look, if we start here, how do we get to there? So we look in each coordinate. Well, I've got to go up by 6 in the first coordinate. Got to go down by 2 in the second. Need to go down by 9 in the third. Focus on the change. The vectors are about the change. So now that's a vector that points in the direction our projectile is going. The next thing we want to do, though, is be careful because we know that vectors have 2 things. They have a direction, but also magnitude. So let's ask the question, what's the magnitude of this vector? So the magnitude of the vector 6, -2, -9, well, that would be the square root of 6 squared plus -2 squared plus -9 squared, which would be the square root of 36 plus 4 plus 81. Now, if you add that up, and remember, when you square negative, it's going to be composite. So it's not, don't make that mistake. Don't lose your signs. Got to be careful. Notice our generous use of parentheses. Parentheses save points. So we want to make sure we use them as often as we need to. All right, 36 plus 4 is 40. Add 81 more. That gets us to 121. Now that's a nice number. Square root of 121, we know that. That's 11. All right. Now what does that tell us? Well, what that tells us is that if we went just along this vector, we would travel a distance of 11 units. Now, is that the right length? No, it's not. what is the right length? Well, what we want to do is we want to go 33 units. Okay. So we say, okay, how do we go from traveling 11 to traveling 33? What's the transition? How do we change it? Well, the key is we take our vector and we scale. So this is our change vector, 6, -2, -9. And we're going to scale by two things. First off, if we scale it by 1 over the magnitude, that says, okay, scale back so it has length 1. Now, it's a vector that goes in the right direction, but only travels 1 unit. Now, after you have that, scale that by 33. So then, we still have the right direction, but now we're going to go 33 units, the exact amount that we want. Well, of course, 33 and 11. Oh, these were nice numbers chosen for us so that we would get a pleasant answer. We like when things work out nicely. All right, so what do we see? Well, this really comes down to 3 times 6, -2, -9, which is 18, -6, -27. Now, is this our new point, and why not? Okay, good. It's not our point. Yes, you got it. Why not? Well, what's wrong with this answer? What is this thing? It's not a point. It's a vector. Okay, since it's a vector, it's telling us something about change. And so this vector here, this 18, -6, -27, that's the vector that gets us to our real destination. So this vector here, 18, -6, -27, that's the vector that will get us from where we start to where the projectile will stop. Well, so now we have our change, and then we say, well, we know where we started. We started at 3, 7, 10. So our end will be at 3 plus our change, 7 plus our change, and 10 plus our change. Whoops. And there we go. So again, 3, 7, 10, that's where we start. And 18, -6, -27, that's how much we change. That's going to be where we stop. So we end up with 3 plus 18, 21. 7 minus 6, 1. 10 minus 27, -17. And that's where we'll stop. And there we go. Good. Good. All right. Well, let's do another problem. So, next problem. Find unit vectors with the same direction as the following vectors. All right. So, we have a bunch of vectors here. 3, -4, t squared minus 2, 2t, and 3, -4, -6. So whenever we want to make something unit vector, we just say we've got to scale by the right amount. So there's really a two-step process. One is, what is the right amount? And two, let's scale by it. So when we talk about the right amount, let's talk about how we find that. That's found by first taking the magnitude. So in other words, we say, well, let's see what the current length is. Now, it might be the case that it's already a unit vector. Probably not. Indeed, we can see that our change in the x direction by itself is already 3. So we're going to be at least changing by 3. Because no matter how much we change in the next direction, it's not like it's going to decrease the change. It can only make it even more change. So definitely this won't be a unit vector. So what is our change? Well, square root of 3 squared plus -4 squared. That's really the square root of 9 plus 16. And nice numbers. Square root of 25 is 5. So that's our current length, which means it's not a unit vector. It's a vector which has length 5. Therefore, to make a unit vector, we will take 1 over the current length times by 3 -4. Now, is this an acceptable answer? Yeah, sure. But another thing you can do is you can multiply it through, and sometimes people like to do that, And you could say, well, this is the same as 3/5 and negative 4/5. And there we go. Good. Okay, well, now to the next one. Now the next one seems a little strange. Because what do we have? Well, we have a vector here, but our vector involves this symbol t. And the question becomes, are we allowed to do that? And the answer is, sure, why not? Why not have some symbols in there? It just says a vector is really a set of changes. Perhaps the t indicates that we change where there's some parameter t that moves along. It's okay to have vectors where we have variables showing up. In fact, it's going to be important the further on we go. So it's good to see it now. So when we see it later, we'll be like, okay, we can handle that. No problem. All right, well, what do we do? Same process. It doesn't change. We take the magnitude, t squared minus 2 comma 2t. So that's the square root of t squared minus 2 squared plus 2t squared. All right, that's going to be the square root of, multiplying that out, t to the fourth, which is the t squared squared, then the cross terms, so that's going to be, normally we say 2ab, so there's going to be a minus, and because there's a 2 there, 2 times 2, so that's going to be really a minus 4t squared, and then plus 4. Square this term, 4t squared. And now we're like, oh, something nice happened here. You see, the 4t squareds cancel out. And now you're like, hey, beautiful. So what we have is the square root of t to the fourth plus 4. Now, what do we do next? Well, the next thing is, we're happy with that. There's nothing we can do more. There's no more algebra to do. You can't rewrite the square root of t to the fourth plus 4 in a simpler way. Because remember, square roots do not work over addition. So don't be like, oh, that's t squared plus 2. No, it's not. Don't do it. Don't do it. Be careful. Be careful. Well, we're almost done. In fact, we pretty much can just write down our answer. We could say, well, that's 1 over the square root of t to the fourth plus 4 times t squared minus 2 comma 2t. So in this case, we could distribute through. I would probably prefer not to. Generally, my rule of thumb is I'll distribute through if it's going to be something reasonable and nice. But when it doesn't really help things look better, I don't see a reason to do it. And so I'll just not do it in this case here. Now, in what sense is this a unit vector? Well, in the sense that if you take the magnitude of it, it would turn out to always be 1. So regardless of your choice of t, this will always have length 1. No matter if you choose t equals 0, t equals 1,000,000, it has length 1. All right. So, well, one more to go. Because these are two-dimensional vectors. And of course, we can do similar things for three-dimensional vectors. Nothing really changes. So if we have 3, -4, -6, and we want to find unit vectors, well, okay, so we find the magnitude of the vector first, magnitude of 3, -4, and -6. Well, that'll be the square root of 3 squared, and -4 squared, and -6 squared, which is really the square root of 9 plus 16 plus 36. Well, 9 plus 16 is 25. We know we just kind of did it a few minutes ago. 25 plus 36 makes 61. Yeah, it does. Sometimes you get a nice square root. Sometimes you don't. That's okay. That's all right. So what do we do? Well, that's the current length. Now we scale back by that, and therefore the answer, the vector we're after, 1 over square root of 61 times 3, -4, -6. And there we go. There we go. Those are our nice, beautiful answers. Beautiful answers. All right. So let's do one more problem. Find the equation of the sphere, which has the line segment joining -2, 3, 7 and 4, -1, 5 as a diameter. Now, let's think about what we mean by a diameter. When we talk about the diameter of a circle, we oftentimes think of it as being a number. And sometimes we say, well, the diameter is twice the radius. It actually has another meaning. When we talk about a diameter of a circle or a sphere, it really means 2 points which are exactly opposite. Now, a nice example to think of is if you have a sphere, let's say, pick the Earth. There we go. That's close enough to a sphere. Then if you took the North Pole and the South Pole, they're exactly opposite each other. That line segment connecting them, that's called the diameter. Okay, good. So now we say, look, I have 2 points, -237, 4, -1, 5. That's going to be a diameter of a sphere. Now what do I know? Well, I know that these 2 points on the sphere, whatever the sphere may be, are exactly opposite each other. So that should be pretty useful to know. How do we transfer that into what we need? Well, for a sphere, we really need 2 pieces of information. We need to know the center and the radius. So if I have 2 points which are exactly opposite each other, what can I say about the center? And the answer is the center is the midpoint. So the center is going to be the midpoint of our diameter. In fact, this is true for any diameter. So it doesn't matter which diameter you pick, it always passes through the center at the halfway point. So this is really a question that gets us towards how do we understand midpoints. Now, for midpoints, it's kind of, there's an intuitive thing, which is sort of like, you average each coordinate. So for instance, I look at my x coordinate, I'm -2 and 4. So what I would do is I'd add them together and divide by 2. So that's sort of like what's the halfway in the x direction is the way to think of it. You take the average of the 2 numbers. 3, add -1, divide by 2. 7, add 5, divide by 2. And if we do that, -2 plus 4, well, that's +2 divided by 2 gives us 1. 3 minus 1 is 2, divided by 2, also 1. And 7 plus 5 divided by 2 gives us 6. So now we have a point that's halfway in between, the center. So this is good. We know our center. Now that's not enough for a sphere. We also need to know another piece of information, which is our radius. But once we have the center, we're good to go. So our center is at 116. Here are some points on the sphere. So what we can do is say that our radius, well, it's the distance between 116, our center, out to one of these 2 points. Does it matter? It doesn't matter. It's going to be the same distance. So we'll just pick one. Let's say we go with 4, -1, and 5. And now we say, okay, so that's going to be the square root of, so 4 subtract 1, well, that would be 3 squared. -1 subtract 1, well, that'll be -1 subtract 1 is -2, so -2 squared. 5 subtract 6, well, that will be 5 subtract 6 is -1 squared. All right, good. So 3 squared, -2 squared, -1 squared. Or if you like, that's the square root of 9 plus 4 plus 1. So the square root of 14. All right, so that's our radius. Now we have our center, we have our radius. Life is good. And we can write down our formula and be done. So what's our formula? It's our x minus our x coordinate of our center, so x minus 1 squared, plus y minus the y coordinate squared, plus z minus the z coordinate squared is equal to the radius squared. Well, our radius is the square root of 14. If you square that, we'll end up with 14. And that's it. That's the answer. We're done. Okay, so here, really it's not so bad as long as we understand the geometry. What does it mean to be a diameter? Where do we find our center? How do we connect things together? And a lot of the problems turn out, once we can start building our geometrical intuition, what does this mean? How do I connect? How do I go from here to there? We can start building up our understanding, and we start having more power, more mathematical ability to work in 3 dimensions. So the important thing is keep practicing. The more you practice, the better you'll become, and the more problems you'll be able to solve. All right, well, I guess I'll see you again soon. Bye.